Hello and welcome to the fourth video of the M2 chapter Centers of Mass. Quick question on the screen to get us started. A uniform triangular lamina has vertices these. Find the coordinates of its center of mass. This starter is just getting us to remember that we need to find the average of the coordinates in order to do this for a triangular lamina. So G, the center of mass, has coordinates 3 plus 2 plus 6 divided by 3 for the x, and 5 plus 7 plus 6 divided by 3 for the y. That gives us 11 over 3 and 18 over 3, which is 6. And there we go. In this video, we're going to find the center of mass of composite laminas. So we're going to be using all of the information from the previous video, keep that in your mind, and we're also going to be using the method that we had in the center of mass of particles arranged on a plane. So we're combining these two ideas to look at more complicated situations. By combining the few uniform plane laminas so far, we can make composite uniform laminas. To find the center of mass of a composite uniform lamina, I'm going to lay out a 4-step process. First, split your lamina into pieces, specifically into the standard shapes that we looked at in the last video. Then locate the center of mass for each section. That's why you need to split it into shapes that we had in the last video, so that you can do this because we know the center of mass for those particular shapes. Third, calculate the relative mass of each section by finding its area. Remember we said for a uniform plane lamina, the area represents the mass. The more area you have, the more mass you have. Then using all that information, we're going to basically do a system of particles on a plane. So we're going to split the shape up into pieces, find the center of mass for each section, find the relative mass, and then pretend that each of those sections that we've split it into is just a particle, which we know the mass of. So we're going to go back to the second video we had in this chapter and treat it all like a system of particles on a plane to find the center of mass for the whole shape. So we're combining some ideas here. In terms of the notes, that's it. And we're going to apply this method to 3 different examples. Our first example, a uniform lamina consists of a rectangle, PQRS, joined to an isosceles triangle, QRT, as shown. Here it is. Find the distance of the center of mass of the lamina from PQ and from PS. So they're not using a coordinate grid, but I will use a coordinate grid to do most of the working out, and then I'll come back at the end and write it in terms of distance from these edges. So the coordinate grid I'm going to use is going to have X along here, and of course Y up here. Step 1. Split your shape into pieces, specifically pieces you can find the center of mass of. So here it's fairly obvious, we're going to split the shape down here. That gives us a rectangle with the center of mass at its geometric center here. For the triangle, we also know where the center of mass is here, and it's an isosceles triangle, so it's a little bit easier because it has here a line of symmetry on top of its median. So we just need to go 1/3 of the way up from the edge, or 2/3 of the way down from the vertex to find it is here. And we have enough information from the lengths shown on the diagram to find the coordinates of these 2 points. Here, this is obviously half of this length for the rectangle, which is 8, so half is 4. If I put on there 4, and half up here is 2. For the triangle, we've got the full length 8, plus 1/3 of this distance, which is 1/3 of this, which is 1. So the x-coordinate here is 9. And the y-coordinate is still 2, because of the symmetry of the shape all the way along here. Now you might have noticed I just said 1/3 of the way up here, or 2/3 down here. This is a case where that actually did help, but I could have done the average of the coordinates. So here, just to show that that will work, we've got 8 for the x-coordinate here, 8 here, and here would be 11. If we add those together, we get 27. Divide 27 by 3, we get 9 for the x-coordinate. Of course, for the y-coordinate, 0 plus 4 plus 2 is 6, divided by 3 is 2. So that will still work. So at this point, we've done step 1, we've split it into pieces. We've done step 2, we've located the centers of mass. Now we need to find the relative mass for each section and put it together in a system of particles on a plane style equation. The way I'm going to lay this out is very systematic, and it'll be the same every time I do a question like this. And it must be fairly standard because the textbook does the same thing. So what I'm going to do is create a little table. I've got a two-way table here. I'm going to have each section of my shape in one of the columns. So I'm going to have the rectangle here, triangle here, and then I'll have the full shape rectangle plus triangle here. I'm going to put a double line down here, just because it's kind of like saying this plus this equals this, and this is sort of like my equals line, just to keep them a little bit separate. The information I need then is the relative mass, the x-coordinate of the center of mass for each shape, and the y-coordinate for the center of mass of each shape. So I'm going to have it like this. A very quick side note on the relative mass. If you go back to video 2, you'll notice we didn't say anything about area in video 2. We were talking about mass. So it's mass that we need in the calculation we're about to do, but it's area in this situation that's going to tell us the mass. So I like to use the term relative mass instead of area or mass, even though area is how we're going to calculate that number. So the area of the rectangle, we've got 8 times 4, 32. For the triangle, we've got 3 times 4 divided by 2 is 6. And for the whole shape, obviously, we just add these two together. So that is 38. One final note on relative mass is that if you write mass here, you could get away with that just by putting in a constant m on each of these, where m would be the mass per unit area. And if you did that and you put it into your equation, all those m's would cancel out anyway. So you could do that if you prefer mass here. Okay, enough on that. Let's keep going. The x-coordinate of the center of mass of the rectangle is 4. The y-coordinate is 2. So we've got a 4 here and a 2 here. For the triangle, the x-coordinate is 9. The y-coordinate is 2. And for the whole shape, the coordinates for the center of mass are the very things I'm trying to find. And as usual, I call that x bar and y bar. Okay, that's step 1, 2, and 3 finished. Now we need to make use of all this information in a system of particles on a plane kind of way. And if you remember back to video 2, the way we did that was to use this formula here. So we had mixi, the sum of the individual bits, is equal to the sum of the individual masses, or in our case relative masses, times x bar. And that's what I'm going to do here. We've got all the information we need here. The relative mass times the x-coordinate of this piece, plus the same thing here, has to equal on this side the sum of the relative masses times this x bar. So as I read it from my table, this times this plus this times this has to equal this times this. And that follows this formula here. So we've got 32 times 4 plus 6 times 9 must equal 38 times x bar. And if you don't want to write the formula out each time, I would write out the individual numbers like this, so it's clear for the examiner what it is you've done with the numbers in the table to get this. And if I put that on my calculator, I get a rather awkward number, 182 equals 38x bar. So we get x bar is equal to 182 over 38, which simplifies to 91 over 19. Then we have to do the same thing for the y-coordinate. So the sum of the individual particles, relative mass times y-coordinate, has to equal the sum of the relative masses times y bar. And again, from the table, it's this times this plus this times this equals this times this. So 32 times 2 plus 6 times 2 equals 38 times y bar, which is 76. And 38 y bar, a much nicer number, because that just divides to give 2. Two things to note here. First is that, as we said in video 2, you don't have to do these separately. you could create a vector equation by using these as position vectors. The second thing is to go back to the question, because again, as we've had in a previous example, this question is not asking for coordinates, it's asking for the distance of the center of mass from particular edges. And while that might match my coordinates that I've used, that's not what it's asking. So while all the maths is finished, I should finish off my question by saying the center of mass is at a distance of 2 centimeters from PQ and at a distance of 91/19 centimeters from PS. A very final note is that the first one should have been really obvious, because there's a line of symmetry across the entire composite lamina here, and we know that centers of mass have to lie on lines of symmetry. So that should have been obvious. I didn't really need to do my calculation there. I should have just realized that 2 was the answer to A. I did need the calculation for B though. Our second example is very similar, but I'm going to use my vectors when I get to doing this part here. The diagram shows a uniform lamina. Find the distance of the center of mass of the lamina from AF and AB. So again, it's kind of using the coordinate grid that I would naturally put on, but at the end of the question I should come back and turn that back into distances from those sides. We'll do that at the end. Here we've got a lot more options in terms of how we split our shape. We could split it here and have this one and this one. We could split it here and have a little square and a long rectangle, or we could even do more than that if we could split it here and here, have 2 squares and a rectangle. Or, which we'll talk about in the next example, I could take the full rectangle around here and then subtract this rectangle here. There's no particular benefit for doing it that way in this case, so I'll leave it to the next example where it's a lot more obvious why you would want to subtract instead of add. But that is an alternative way of doing it. What I think I would like to do is to split this into a square. Center of mass here. The big rectangle has a center of mass here. The coordinates of that are 4 and halfway up here. This is 2, so this must be a 1. And here, this is 6, this is 8, so this is 2, half of that. This must be a 1 on the x-coordinate here for the square, and 3 here. So I've split my shape, I've located the centers of mass of the individual sections. Now I'm ready to do my table. So again, I've got a small piece, other small piece, and then the full shape together. Relative mass, which I'm going to calculate by finding the areas, and then the x-coordinate and the y-coordinate of the center of mass of each shape. Area of the square is 2 times 2, that's 4. The area of the rectangle is 8 times 2, 16, so the total area is 20. The square has center of mass coordinates 1, 3, and the rectangle 4, 1, the full shape x bar, y bar. Now I'm ready to form my equation as if they were particles on a plane. I'm going to do mass times this position vector, mass times this position vector, add them together, and that has to equal this mass times this position vector. So we've got 4 times 1, 3, plus 16 times 4, 1, equals 20 times x bar, y bar. That gives me 68 and 28. I'm running out of room. X bar, y bar. So if I finish up here, x bar, y bar must equal 3.4 and 1.4. Now again, back to the question. They want the distance from AF. AF is this side, so that's the x-coordinate, which is 3.4. So my answer for A is 3.4 centimeters from AF, and for B, 1.4 centimeters from AB. And don't rush that part, because it might have been, instead of AB, it might have been something like DC. and that would not be 1.4 centimeters, that would be 0.6. So just take a moment and make sure that the question is asking you what you think it's asking you. Our final example, you can see, is a little bit different. A uniform circular disc, center O of radius 5 centimeters, has 2 circular holes cut in it, as shown. The larger hole has radius 2 centimeters, and the small one 1 centimeters. The coordinates of the centers of the holes are given to us. Find the coordinates of the center of mass of the remaining lamina, the bit in blue here. Now don't panic, we're going to do exactly the same as we did here, but instead of adding the pieces together, we're going to subtract. We're going to have a big circle, and then we're going to subtract the big hole and the small hole, and we're still going to have on the end here the shape that we actually want. So I'm going to jump straight into the table here because we've got a lot of the information given to us in the question. So my table is going to be a little bit longer. I've got an extra piece to it this time. I've got the big circle without any holes, and that's going to be subtracted by the big hole and the little hole. My little diagrammatic idea here isn't really very clear when they're all circles, is it? And that is going to have to equal this thing with the holes cut out. So let me say again, the main difference here is that we're going to start with this without any holes cut out of it, and then we're going to subtract these two instead of adding. Everything else stays the same. We still need the relative mass and the x and y coordinates of the centers of mass for each piece. I know straight away x bar and y bar down here, they're the things I'm trying to find. We also know straight away the centers of the holes. And remember, for a circle, the center of mass is at its geometric center. So although it might seem a bit strange because these are holes, they're not laminas, I have to treat them as laminas because that's what I'm taking away. If you prefer, think of this as a separate disc before it's been punched out, and when I take it away, it leaves a hole. But the center of mass of the disc that has been taken out is at 0, 2. That's the big hole. The little hole is at 2, minus 2, and the full circle with no holes cut in it has a center at 0, 0. I need the relative mass, which means the area. The area of the big one is pi r squared, where r is 5. So we've got 25 pi here. The big hole has a radius of 2, so that's 4 pi. The little hole has radius 1, so that's just pi. So now I come to work out the relative mass of the final shape. And here, again, I've got to remember that I'm subtracting these pieces to make holes. So it's 25 minus 4 minus 1 is 20 pi. Now I form my equation using the system of particles on a plane, but subtracting instead of adding. So I've got 25 pi times the coordinates of its center of mass, minus 4 pi times the coordinates of its center of mass, minus pi times the coordinates of its center of mass, is equal to 20 pi times the coordinates x bar, y bar. And there are quite a few zeros floating around there, so it makes it quite easy. We get minus 2 pi here, minus 6 pi here, equals 20 pi x bar, y bar, which cancels to give minus 1 over 10 and minus 3 over 10 x bar and y bar. The center of mass then of my final shape, the coordinates minus 1 over 10, minus 3 over 10. I hope that's enough for you to have a go at some of these in exercise 3D, and maybe I'll see you for frameworks in the next video.